Welcome to Visual Algebra Lecture 3.5, Subgroup Diagrams. Conjugation is an equivalence relation on the set of subgroups of a group, and the equivalence classes are called conjugacy classes. In this lecture, we'll introduce an object that we call a subgroup diagram, which is basically a subgroup lattice collapsed by conjugacy classes, but it need not be a lattice. This allows us to see patterns that subgroup lattices can hide, and to visualize the subgroup structure of some really large groups. We'll also show that the size of a subgroup's conjugacy class is equal to the index of its normalizer, and we'll interpret this in terms of Cayley graphs, subgroup lattices, and subgroup diagrams. Along the way, we'll see subgroup diagrams of the three smallest nonabelian simple groups, as well as the 71st smallest, whose order is over 2.5 million. This is going to be fun. So let's get started. Let's begin by verifying that conjugation is an equivalence relation on the set of subgroups of a group G. To prove this, we just need to show that conjugacy is reflexive, symmetric, and transitive. Reflexive just means every subgroup is conjugate to itself, and that's straightforward. Just use the identity. For symmetry, let's suppose that H is conjugate to K via A, so AH, A inverse is equal to K. Well, then K is conjugate to H, just use A inverse. A inverse KA is A inverse times AH, A inverse A, and the A and A inverses cancel, and we get H. Finally, for transitivity, let's suppose that K is equal to AH, A inverse, and L is equal to BK, B inverse. So H is conjugate to K, which is conjugate to L. Well, then H is conjugate to L. And you just conjugate it first by A and then by B, or I should say by BA. And when you do that, you first conjugate by A and then by B. The set of all subgroups conjugate to H is called its conjugacy class. And we will write this as CL sub G of H. And formally, that's just the set of all GHG inverse, where G ranges throughout the group. Sometimes it is convenient to collapse conjugacy classes into single nodes in the lattice. When we do this, we will denote the size of the collapsed conjugacy class with a left subscript. We call the resulting diagram a subgroup diagram. We know that it need not be a lattice. So in this particular case, this is the subgroup diagram of A5. Here are two nodes representing conjugacy classes. And in a lattice, that means that there must be a unique minimal element containing both. But here are two incomparable conjugacy classes that contain both. So this cannot be a lattice. Now that said, several sources use these, and they call them subgroup lattices. I first saw these in the group names website, maybe in the mid to late 2010s. I don't know when it was published first. And it's also used by the LMFDB in the early 2020s. And I know group names, they call these the subgroup lattices because it really is a subgroup lattice. It's just kind of a compact form of it. But I want a term that distinguishes something like this to an actual lattice where you see all the groups. So that's why I call it a subgroup diagram, and I hope this term catches on. Now, for this particular example, we can see that this group is simple. Remember what that means? It means that the only normal subgroups are G in the trivial group. So looking at here, all of the intermediate nodes are conjugacy classes that have size bigger than 1. So that means that they cannot be normal subgroups. Normal subgroups, remember, are in a unique conjugacy class, and so in a subgroup diagram, we will never actually write a subscript. So just like A5 or C1. Here is the subgroup diagram of an utterly enormous group. It has order over 2.5 million, and it has over 1 million subgroups. This one conjugacy class has 431 some thousand subgroups. But they fall into just 20 conjugacy classes, which I find remarkable. First of all, this should exhibit the utility of these things. There's so many groups that we can't even visualize structurally otherwise, but we have some insight. And I think it's really neat to look at this little motif, and that looks like a Klein 4 group. But it's not really, because these subgroups are not normal, so you can't take any sort of quotient by them. But the pattern is still there. Should also mention that this group is simple because all of these intermediate conjugacy classes have size bigger than 1 because they all have left subscripts. So the only normal subgroups are G and the trivial group. And this is how I actually found this example. I went to the LMFDB and I looked at the list of nonabelian simple groups and just looked at how many subgroups and conjugacy classes they had. And I noticed that there's this really, really big one that had very few conjugacy classes, a lot less than I expected. So I clicked on it, and sure enough, the subgroup diagram was on there. It wasn't as nicely organized as this, so it was hard to get this to fit on a page, but I did, and here it is. Subgroup diagrams can reveal patterns that are otherwise hidden or at least obscured in the subgroup lattices. As an example, here are the subgroup diagrams of the dihedral groups, starting with D4, which we've seen before. Remember, there's 2 subgroups here and 2 over here. These are generated by the 2 side bisecting reflections, and the other 2 are generated by the 2 angle bisecting reflections. And I think the pattern here should be obvious. You could make D32 on your own. And here's the pattern for D2. So remember, D2 is, if we take the presentation for the dihedral group, R and F, subject to R squared equals F squared equals 1, and R equals F, we actually get the Klein 4 group. And geometrically, you can think of this as the symmetry group of like the two-gon, which is like this little sector, which is, of course, the symmetry group of the rectangle. Here are the subgroup diagrams of the generalized quaternion groups. What do you notice? Well, don't they look like the dihedral groups on a stick? Why is that? Well, remember, all of these contain a subgroup generated by -1, which is normal. And remember that when n is a power of 2 in the dicyclic group, we get a generalized quaternion group because every cyclic subgroup here contains -1. So every subgroup, well, non-trivial subgroup, will contain -1 as well. So that's why these are sitting on a stick. But also, why do these things look dihedral? Well, that is because the quotient of the quaternion group by the subgroup is isomorphic to a dihedral group. Well, what's the subscript? So here we have Q8 mod. Again, we haven't formalized this yet. This is going to come in chapter 4. But I'm dropping all these hints about how when you see familiar subgroup lattices sitting at the top of a lattice, that's a quotient. So this subgroup lattice is D2. So here we have Q16 mod -1 is isomorphic to D, that's D4. And so in general, this is going to be dn over 4. Subgroup diagrams really highlight conjugacy classes and especially their size. So I want to take a few moments to make a connection between that and the normalizer of the subgroups. And I'm going to revisit the example of A4 from the previous lecture. So please watch that if you have not already. Here are 3 Cayley graphs for A4, each highlighting the left cosets of a different subgroup. Over here we have N, here we have K, and here we have H. And remember my convention. I will draw a left coset blue if it is also a right coset. That means that the normalizer is the union of the blue cosets. So N is normal because all 3 of these left cosets are also right cosets. Equivalently, the normalizer has index 1 because it is equal to the entire group. We say that N is normal. K has 6 cosets, and 2 of the left cosets are right cosets. So its normalizer has order 4. It means the normalizer has index 3 in the subgroup. So we say it's moderately normal. Remember, the worst case scenario would have been that only K itself is a right coset. And that's what happens for this subgroup H. H has index 4, so there's 4 cosets, and H is the only left coset that is a right coset. This is the worst case scenario. We say this is fully unnormal. So the index of the normalizer of H, which is equal to H, is equal to 4. So remember these numbers, 1, 3, and 4. They are in some sense measuring how unnormal, how far away or close a subgroup is to being normal. Here is a subgroup lattice of A4. N is in a conjugacy class of size 1. K is in a conjugacy class of size 3. And H is in a conjugacy class of size 4. Observations. A subgroup is normal if and only if its conjugacy class has size 1. And the size of a conjugacy class tells us how close to being normal a subgroup is. So the wider this is, the more conjugates there is, the further it is from being normal. And finally, do you recognize these numbers? 1, 3, and 5? In all of these cases, the size of the conjugacy class is the index of the normalizer. And in the previous lecture, I gave that a name. I called that the degree of normality. So again, please watch that. That term is unique to my video series and my book. And it's just the proportion of cosets that are blue. We can formalize this as a theorem. It holds more generally. For any subgroup H of G, the size of its conjugacy class is equal to the index of its normalizer. Remember, the more things a subgroup is conjugate to, the less normal it is. And the more cosets that were not blue, the less normal a subgroup is. So these are measuring degrees of normality, but they're actually measuring the same thing. Here's a picture for what this means. So here's H, a subgroup, and it's got a few other cosets that are in the normalizer, maybe, or maybe not. But if you conjugate H by anything in the normalizer, by definition, you get back H. Let's take another coset of the normalizer. Let's say it contains an element A. So if you conjugate H by A, well, you get A, H, A inverse. And the claim is that this, well, it has to be different from H because A does not normalize H. Let's take another coset, BH. So it contains an element B. If you conjugate H by B, you get BH, B inverse. This also cannot be equal to H because B is not in the normalizer. But I claim it's not equal to A, H, A inverse either because it's in a different coset. So the cosets of the normalizer, doesn't matter what you pick in any one of them, if you conjugate by that H by something in there, you're going to get the same thing. You guys see that? So over here, conjugate by anything in here, you're going to get Z, H, Z inverse. Let's talk about how the proof of this will go. I don't know if I can quite fit the whole thing in the margin, but I can get close. So we need a bijection between the cosets of the normalizer, because that's what the right-hand side counts. The index of the normalizer is the number of cosets, and the conjugate subgroups to H, which is just the conjugacy class. So let's define a map from the cosets of the normalizer to the conjugate subgroups of H. And how are we going to define that? Well, here is that map. For any coset X, I'm going to call N the normalizer just for short. So Xn is going to get mapped to X, H, X inverse. This is how I'm defining phi. Now we have to show that this is well defined. and then that it's a bijection, 1 to 1 and onto. So first, let's show well-defined. What does that mean? That means that if we have two cosets that are the same, suppose that xn equals yn. So in other words, suppose that you have one of these cosets and you have x in here and you also have y in here. Well, then this map is going to send, if you use this representative, it's going to send it to xh x inverse. If you use this one, it's going to send it to yh y inverse, and those better be the same. And if those are in the same coset as b, then that better be equal to bh b inverse as well. So we have two cosets that are the same. We have to show that the conjugate subgroups are the same. So what does it mean for the cosets to be the same? Well, that means y inverse x n equals n. And what does that mean? That means that is equivalent to saying y inverse x is in n. In other words, y inverse n normalizes h. So y inverse x times h is equal to h times y inverse x. Okay, now what from here? Well, we're almost done. Let's move the x over here and the y over there. So we can write this as xh, again, x inverse equals yh y inverse. You see how I multiplied both sides by x inverse on the right and by y on the left? And that's what we wanted to show. Any two elements in the same coset, the corresponding coset will get mapped to the same conjugate subgroup. Okay, so what about onto? So I'm going to use a different color. Why is this map onto? Well, of course it's onto. If you take a conjugate subgroup, xh x inverse, then it came from the coset xn. So that's just immediate. And then what about 1 to 1 or injective? Oh, what does 1 to 1 mean? Remember, well-defined means that if you have two cosets that are the same, say xn, that happen to be equal to yn, then they have to get mapped to the same thing. So in other words, you can never have that little diagram. You can't ever have the same subgroup getting mapped to two different things. That's not allowed if it's well defined. And then 1 to 1 kind of means the opposite. It says if you have two things, I'll do it up here, xn and yn, that get mapped to the same thing, same z inverse, then those things need to be the same in the first place. So in other words, we never have this little two things get mapped. We never have this little motif at all. So it's kind of the dual of well-defined. And in this case, we can just run this argument backwards. So let's write that out. So 1 to 1, let's say that phi of xn equals phi of yn. Oops, I ran out of room here. Equals phi of yn. See if I can fit that there. What does that mean? That means that xh x inverse equals yh y inverse. Okay? And what are we trying to conclude? We're trying to conclude that if that happens, then these two cosets were the same in the first place. So two cosets get mapped to the same thing, then those cosets had to be the same. So we need to somehow conclude that xn is equal to yn. So how do we do that? We just run this in reverse. We are starting here. that the two conjugate subgroups are the same. This is equivalent to y inverse x h equals x y inverse h. This is equivalent to y inverse x normalizing h, or being in the normalizer, which is equivalent to y inverse x n equals n. And that you move the y over here, that's equivalent to those two cosets being the same. So there's the proof. It's worth mentioning that later in this chapter, we will do a very analogous statement for the size of the conjugacy class of an element and the index of a subgroup called its centralizer. Then in chapter 5, we will generalize both of these in something called the orbit stabilizer theorem. If we have a group action, which is a group that rearranges a set of objects, in this case it rearranges subgroups by conjugation, then the size of the orbit, which is a generalization of the conjugacy class, it's what things get mapped to under that rearrangement, is the index of a subgroup called its stabilizer. And their proof is basically the same. I'm going to have a picture just like this both later in this chapter for conjugacy classes of elements and centralizers, and also in chapter 5 for group actions and stabilizers. Here is that same theorem that we just proved, or at least this first part is. But now I want to assume that h has finite index because I'm going to talk about fractions. So let's suppose that h is a subgroup of index n. Then the size of the conjugacy class of h is the index of the normalizer. Remember, this is how many cosets the normalizer has. So in that little picture we had something like, this is h, and maybe this is the normalizer, the blue cosets, and then there were other cosets, something like this. So the index of the normalizer is how many cosets there are, and this is saying if you take the total number of elements in G, for a moment, imagine G is finite. I should probably add that. So let's just assume that everything is finite. Take the total number of elements in G and divide it by the number of elements in the normalizer. Well, that's the number of cosets. And that's equal to 1 divided by the degree of normality. Remember, we defined this in the previous lecture, and we saw it again earlier. It's not something I always want to go back to, but it is helpful to have this idea. And here's that idea down here. So if n is a normal subgroup, then the size of the conjugacy class is 1, which means that the index of the normalizer is 1, because yes, the normalizer is all of G by definition. If K is moderately normal, like we saw with A4, then the normalizer is strictly between K and G. That's what it means to be moderately unnormal. Normalizers can't be G because it's not normal, but it's bigger than K because of the moderately part. So if this has M subgroups, then this normalizer has index M. And then finally, the fully unnormal part is when the normalizer of H is equal to H itself. So given this assumption of H having index n, the normalizer has index n, and that's the size of the conjugacy class. So in this case, remember the degree of normality was the proportion of cosets that are blue. So in this case, if there's like 1 over m, so well over here, 1 over n cosets are blue. That's and this is the degree of normality. Over here, 1 over m cosets are blue. And here, 1 over 1 are all cosets are blue. So 1 divided by that fraction is 1 divided by the degree of normality is the number of cosets. Using that last slide as an example, the set of all conjugate subgroups to H looks like a fan in the lattice. So we have H, X inverse, and maybe there's others, and it's like a fan. However, not all such fans comprise a single conjugacy class. The big idea is that a wide fan means the subgroup is very unnormal and has a smaller normalizer. A narrow fan means that the subgroup is closer to being normal and has a larger normalizer. If the subgroup is normal, then the fan is as narrow as possible, size 1, and the normalizer is equal to G. The following says that the base of a fan is always normal. So what do I mean by the base of a fan? So if you have a subgroup H and you have its conjugacy class, you intersect all these elements, you will eventually get a subgroup. Now, I don't mean to say that there's no intermediate subgroups here. There very well might be subgroups somewhere in this middle part, but you can define the intersection of these, and that will be a subgroup that I call the base of the conjugacy fan, and that is normal. And it's an exercise to verify this. Let me just say a few words about that. So how would you show that? Well, let's suppose you conjugate. So show that Gn G inverse is equal to n. Well, take Gn G inverse. And so what is that? So Gn G inverse is just the intersection of all these conjugates. In other words, what happens if you conjugate all of these subgroups by G? Well, you're just going to permute them amongst each other. And so when you intersect them as a set, you still get the same thing. You got to check a few details, but that's basically how it goes. There's actually one more thing you can say. You can say not only is n normal, but I claim n is the largest normal subgroup containing H. So n is the largest normal subgroup containing H. And why is that true? How would you show that? What does that mean? Well, it means if you take some k that's normal in G with k containing H, then k has to contain n. So how do you show that? Let's take k, which is a subgroup of H. And what happens if you conjugate k by something? Let's take gk G inverse. Well, k is normal. So that's equal to k. And this is contained inside of G H G inverse. So we can conjugate k to be inside of any of the conjugates of H. So let me now erase these up here. So if I have k down here and I conjugate by G, or let's not say J, let's say H2, k H2 inverse, then that must be in here. But that's equal to k. And that's equal to xm inverse k x inverse. So every conjugate of k's, you can move it to be inside of every single one of these, which means it has to be in the intersection of all these, which means it has to actually be in n itself. So if k is any normal subgroup contained in H, it's got to be contained in all of the conjugates, and therefore in the intersection of the conjugates, which is n. Therefore, n is the largest normal subgroup containing H. This proposition places strong restrictions on the lattice structure of any simple group. In other words, that the intersection of the conjugate fan, or the base of the conjugate fan, is normal. Let's take a look. Here is the subgroup lattice of A5. I started this lecture with the subgroup diagram. Here's the full subgroup lattice. Let's take a conjugacy class up here. The base of this conjugacy class has to be normal. Well, there's only two normal subgroups. This is simple. A5 and the trivial subgroup. So the intersection of these 5 subgroups has to be trivial. Similarly, the intersection of any of these conjugacy fans has to be trivial. So there's no bases. None of these intersect like in a group down here. So the full subgroup lattices of the simple groups look like, you got these big conjugacy fans, and so, sometimes they have a single subgroup underneath them of another conjugacy class, and sometimes there's multiple ones. But they all kind of spread out, and all of these intersect in the trivial group. They basically look like this, but only bigger and more complicated. I don't know about you, but for me, I find that helpful. Like, this is what nonabelian simple groups look like. Finally, I want to say a few words about how we can spot the normalizers, at least in this case, just by inspection. Of course, the normalizers of the two normal subgroups have to be the group itself. So let's look at one of the intermediate conjugacy classes. Let's take one of these A4 subgroups. This is not normal, and the normalizer has to contain it. So the only other possibility is that the normalizer is itself. So I'm going to put a little arrow from each subgroup to its normalizer. Notice how the conjugacy class is size 5, and that is the index of the subgroup and also the normalizer. What about these V4s? So this V4 here is also in a size 5 conjugacy class, so its normalizer has to have index 5, so it's up here. But it's only contained in one subgroup in this class, so the normalizer has to be A4. Okay, let's go over here. D5, or any of these D5s are contained in a size 6 conjugacy class, which is the index of itself. So each of these has to be its own normalizer. That was also forced because this is non-normal, and there's nothing intermediate that the normalizer could be. Going down to the C5s, this C5 is also in a size 6 conjugacy class, so the normalizer has to be the D5 that contains it. Going over here, these S3s are, well, without even counting how big this is, I know there's 10 of them because that's the index of each of these. So once again, this S3 has to be its own normalizer, size 10 conjugacy class, index 10. And then down here, these C3s are also in size 10 conjugacy classes, in a size 10 conjugacy class, so the normalizer of each of them has to be the unique S3 that contains it. Okay, what about these C2s? So these C2s are in a size 15 conjugacy class. Well, this first C2, well, suppose we didn't want to count that. What's the possible normalizer of this? Well, what's the index of these things? Well, these things have index 30, right? 5 times 3 times 2. And so what contains these C2s? Well, the V4s, the A4s, and a couple of the S3s. Well, this is bigger than size 10. I can just tell by inspection. So the normalizer cannot be up here. So the normalizer has to be, I think, up here. And these groups have index 15. And yep, this looks like there's 15 subgroups. I don't need to count them. I know it's more than 10, and it's not 30. So the normalizer of this C2 has to be the unique V4 that contains it. And you can do this with any element in the conjugacy class. I just picked one, but I think it's really cool how we can find the normalizer just by inspection using our theorem without actually computing anything other than just the product of the indices. Here is the subgroup diagram of the second smallest nonabelian simple group. This one has order 168. The subgroup lattice is just too big and too messy to draw on here. Notice here are size 28 conjugacy classes. Let's do the same thing we just did. For each of these conjugacy classes, let's figure out what the normalizer is isomorphic to. So how do we do this? Well, let's start down here. So these C2s, or each C2 is in a conjugacy class of size 21, so its normalizer has to have index 21. And what that means, it has to be a D4. So I'm going to put an arrow up here. What about the C3s? The normalizer of this has to have index 28, so that has to be as one of these. And again, I don't know, I'm going to just guess from experience that each of these is contained in a unique subgroup up here, but I don't necessarily know. Well, I do know that because each S3 has a unique C3 subgroup. Okay, so similarly, the C4s are in a size 21 conjugacy class, so their normalizers also have to be D4. These things, both of these V4s are in size 7 conjugacy classes, so their normalizer has index 7. Now, we don't necessarily know if which conjugacy class of S4 they are. So maybe there's something I can deduce that, but right now I don't know if the normalizer of this V4 is going to be this one or that one. What else? C7 is going to be in a size, the C7s are in a size 8 conjugacy class, so their normalizer is going to be each normalizer, or the normalizer of each of these is going to be one of these, index 8, 8 and 8. This is the size 7 conjugacy class, so the normalizer will have index 7, so there's only one of those that contains this. And similarly, the normalizer of one of these A4s has to be this S4 right here. And then these things are maximal conjugacy classes that are not contain normal subgroups, so each one has to be its own normalizer. So is there anything else I skipped? Is there anything we can say about this V4? I don't think so. So I just holistically, I think that one of these V4s is probably the normalizer is going to be one of these, and the other one's going to be the other. And if I had to venture a guess, I would, you know what? I think I can say something. I think I can say that A4, we know, has subgroups that are V4. So there's a unique normal subgroup. So A4 has to contain, this A4 has to contain, or each of these A4s has to contain a V4 subgroup. So I think these things are contained in there, which means that they're not contained in there. And so I'm going to just venture a guess. I'm going to use blue. That I bet that the normalizer of this is up here, and I bet the normalizer of this is up here, because these things are contained in here, which are contained in here. Of course, these things are also contained in here, but I just holistically think that these things their normalizers are going to be up here. And that's not a proof, that's a hunch. Here is the subgroup diagram of the third smallest non-abelian simple group. I will let you do the exercise I just did of figuring out for each subgroup, or for one subgroup in each conjugacy class, what the normalizer is isomorphic to. And finally, here's that subgroup we saw in the beginning. Since I just showed you the subgroup diagrams of the first, second, and third smallest non-abelian simple group, well, here is the 71st smallest non-abelian simple group. And you can do the same thing. You can take one of these conjugacy classes and say, well, what about a subgroup A4? What is its normalizer? Well, it has to have index 21, 5, 7, 31. Well, that actually, it has index. So this is its own normal. Each one of these is its own normalizer. These are fully unnormal subgroups. And you can keep going with it. I actually put this on a graduate level algebra exam. You can go on my website and take a look at it. There's a whole bunch of questions that I asked about this subgroup, not just involving conjugacy classes and normalizers. There's other things. And I think it was a bit of a surprise when students opened it up and they saw a subgroup lattice of a group this big. And that is a good place to stop. In the next lecture, we will continue looking at conjugate subgroups. It's actually titled conjugate subgroups because we will prove some things algebraically about them, and then we will explore what they look like visually in Cayley graphs. And we'll learn about a mathematical term that I call a unicorn. You won't want to miss that, so stay with us.